right, can I get some thumbs up on screen if people can hear me? Okay, good, thank you. Just making sure everything's hooked up and ready to go. Let me share my screen. We're gonna jump right into things today. We've got a lot to cover. You may have heard me talk about before kind of repacing the materials. We've tried to intentionally slow down the rate at which that we're covering, that we're traveling through these materials, the rate we're covering the beginner Python materials. And I think overall it's been a success. I think it's left me some room to explain things more. I'm kind of happier teaching the materials. It seems like it's landing well for everybody and people are enjoying it. So I'm kind of assuming, just from what I'm hearing with people, from interactions with people, that it's going well and that it's working well for folks. One slight issue is that today I was talking with Tovio and kind of talking through things. I have to get through dictionaries and sets today, so I'm going to be very much on a schedule. So bear with me if I go a little fast. Feel free to still ask questions. It's still open for questions and everything. As much as you want to ask, I may reserve the right to just kind of charge forward, though, depending on what things are. So that being said, I think we can do it. I think we can get through this material thoroughly today and have some stuff left over for next time. So let's finish up dictionaries, then we'll get into sets. Sets will be part of what Tovio is going to go over, I think, next lesson or at some point this week. So we'll get through those at the end of this. And if we're lucky, we'll have time for tuples at the end too. Okay, so last time we talked about dictionaries. So a dictionary is, let's come back up to this definition up here. We won't go through everything again, but quick definition of a dictionary. We'll give an example. A dictionary is somewhat like a list, whereas lists have indices that are numbered starting at 0 and automatically inferred based on the number of elements in the list in order, right? So the elements of a list retain their order related to their position, and the index relates. The index relates back to their position. So since they retain an order, it makes sense to give them an index. So dictionaries we think of as an unordered type. I did some researching and I was talking about dictionaries being an unordered type and saying like sometimes you'll print them out or loop through them and they will at certain times not retain an order. I think it's still useful to think about dictionaries as a type whose order you can't count on in general, but as of recent updates, dictionaries do retain the order that you place items in them. You can't change that order. So there's no like moving them around without just creating a new dictionary and adding things in the order that you want them. So for that reason, we still don't really think about them as an ordered type. Also, if I do like a dictionary with like A, B, let's give these some values. We'll do 10 and 20. So if I do this and I compare it to a dictionary like B20, A10, this will be true, right? So even though the order is different and the order is now retained, we don't think about them as having that same kind of order. So you can see that that's true, right? So even though now order is retained, when we compare two dictionaries that have the same key value pairs, even if the order is different, they're still considered equal. They're still considered the same value. So that's something that's worth bearing in mind. So the keys must be immutable. We can use any other data type for a key. It could be an integer, any other data type, so long as it's an immutable type. So we could be an integer or a float or a string. It could even be a Boolean, or I guess it could be none or something, but generally what we'll do is we will have strings or numbers are the most common forms of keys. But we can't have lists. We can't have dictionaries as keys in a dictionary. We can have lists or dictionaries or any type as a value. So we could put any type we wanted as the value for any key in the dictionary. So yeah. So back to the definition. So dictionaries contain key value pairs rather than index and element pairs. You could think about it sort of like that. So a key is very much the analog of an index and a list. It's just the way that a dictionary goes about getting that key is different than the way a list goes about getting a new index. So dictionaries contain key value pairs in a mutable, unordered collection. Unordered, maybe you want to put an asterisk after unordered, but mutable, unordered collection. So keys must be immutable and unique meaning we can't have multiples of the same key. If I try to overwrite a key, it'll just put whatever new value I associated with in the key that's already there. There will still only be one of that same key. Dictionaries are declared using curly brackets. See above here. It's an example of two dictionary literals. And there's an example of the syntax. So notice the syntax. We surround the dictionary in curly brackets, and then we write the key, whatever key we want, and then a colon, and then a value. So key, colon, value, comma. That's one key value pair. Key, colon, value, comma. That's the second key value pair. Key 3, colon, value 3, etc. We talked about accessing elements in a dictionary. So I'm going to do the car thing again, just because I think it's a fairly intuitive analogy. So let's do make. We'll do Toyota again. And model and year. Model. Let's see here. Year. Okay. Let's say we'll print car. So there's the whole car. If I wanted to print the year, I could say car sub year, like that. Same with all of those. So this is how I can read out elements. If I wanted to reassign the year, I could say car sub year. So D sub year, dictionary sub key, and then D sub key equals, let's say 2014. Now when I read out year, the value at year, I'm going to get 2014. So that's create dictionary, create or update an existing field. We can, let's do another one. Let's create a new field. Let's say car sub color. Car sub color equals black. Okay, and then there we go. So you can see now that contains color. So this is reading out values here, creating new key value pairs, updating existing key value pairs, declaring a dictionary with elements, obviously declaring an empty dictionary. Hopefully it's obvious. I say obvious, but hopefully it's obvious. Creating a new empty dictionary like this. If you wanted to, you could create a new empty dictionary and then kind of go. You could populate it like this. Let's say that. Let's say equals, and like that. Okay. Not sure why you'd do it this way, but if you wanted to, it's your code. Just another variation on that. Okay, cool. Moving forward. Any questions to this point? I do see one in here. Is there a limit to how many key value pairs can be in one dictionary? Not to my knowledge. In fact, I'll say I'm certain that there's not. I don't I can't think of anywhere that's ever said that, but I would be shocked if there was some upper limit to how many could be in there. I think it would just be, the limit of what your computer's memory is, which is, I've got, if y'all have probably got like at least 8 or 16-ish gigs. Even if you got 4, that's a very big dictionary. So even 1 gig. Cool. Any other questions? So this is all kind of foundational. What I'm going over here is all foundational. Creating a dictionary, adding in key value pairs like this. D sub new key equals new value. D sub old key equals new value. Printing off the whole dictionary, accessing the whole dictionary, accessing a given value, right? So looking like everybody is good. If you have another question regarding this stuff, do feel free to put it in there, because this is foundational, so I want to make sure we're really solid on this stuff. Methods. So we talked about some dictionary methods. This will be a quick recap. Well, shoot, why don't I just use this one? When you're working with dictionaries, often you're going to want to ask yourself, am I trying to work with the keys, just the keys, the values, just the values, or both key values, right? So when you're iterating through a dictionary, if I want to iterate through this dictionary, I probably want to iterate through the keys and the values. So I could say for excuse me, for K, comma V in car dot items. If you don't know whether you should iterate through only keys or only values, don't even think about it. This is not a problem that you need to spend any time thinking about it. Just assume that you need to iterate through both, and just iterate through both. If you get through your problem and you find, you can always look back and say, well, there's one of these that I didn't use in the for loop, and you could say, oh, well, I only used the values, so I'll say values. And then you can delete key from there and clean up your code a little bit. But unless it's like totally obvious to you in the moment that you only need one, if there's any confusion whatsoever, just iterate through dot items, and that'll give you both. So I could do print, we'll do an F string, K, dang it, oh my gosh, I keep hitting that key. Wonder if I'll ever learn to not hit that key. There we go. Keyboard key, not dictionary key. Okay, the key is K. Oops. The value is, there we go. The key is make, the value is Toyota. The key is model, the value is Highlander, etc. I can do whatever I want to, whatever I need to do with this dictionary in the loop. So for iterating, we are going to usually use items. Often when you're doing a check for membership, you're either checking membership of keys for the purpose of possibly adding in a new key value pair, or you're checking membership of values for some other purpose. So when you're checking membership, you might say let's do make in car dot keys. Now, the astute among you, and I mentioned this before, the astute among you may observe that I don't need to do keys there. I can do this, and it's exactly the same as doing keys. Some of you might think, oh, well, maybe one is slightly different. There's a reason to do, like it works slightly differently, but they're basically the same. No, they're exactly the same. These two lines are exactly the same. It is typical that when you go read code out on Stack Overflow or Reddit or whatever, you see people posting code maybe to other people's questions or maybe to your questions. If they check for membership in keys in a dictionary, they're going to leave this off. I'm going to leave off dot keys there. So this is the standard way to do it. This is, I think, it might even be the PEP8, might be specified in PEP8. I'm not sure. I kind of think it is. I always prefer to do this, and I encourage that you do this, at least for now, like while you're starting off. I think it's more explicit. I think it reads more, it's just a little clearer. But it is important to know that these behaviors are the same. So we can check keys that way. So let's say engine size and keys. So we don't have a field for engine size. Let's say make. Let's see if make is in values, and let's see if Toyota is in values. All right. Let me do this. I'm just going to do this really quick to kind of mark these so we can at least see which one is which, because we've got a few true falses. Okay, cool. There we go. So is make in keys, that's true. These lines are exactly the same. Engine size in keys, that's false. Make in values, that's false. And then Toyota in values is true. Cool. I see a couple questions, or it looks like maybe just one question. Could I talk about Python dictionary comprehensions? I'm going to mention this rather quickly. So there are list and dictionary comprehensions, and they are short forms for doing that. They're short forms for doing list or dictionary accumulator problems that you can do with a for loop anyways. Comprehensions are really cool, and they can be an optimization. There are ways that they can be optimized, but they are technically a little bit more limited in what they can do than doing a very standard accumulator in a for loop. And for now, I would rather you all practice standard accumulators to get that pattern ingrained. The reason is if you get really solid at the accumulator pattern, you're kind of unstoppable. There's not a lot you're not going to be able to do with for and while loops and accumulator patterns. Some problems aren't solved with accumulator patterns, but honestly, I've done a variety of different kinds of coding, and at some point I find myself just grinding out different accumulator patterns, and If I'm not doing that, then I'm using a library, and under the hood of that library, I know that code is being implemented using accumulator patterns. So it gives me a sense of how other code that I'm using works. And it's sort of a foundational sort of algorithmic thinking pattern. We will get into comprehensions. I want to save those for Saturday. I don't think we'll have time to really get into those today. But just know if you see comprehensions, they're really neat, but they don't actually teach you anything. They don't actually give you a skill that you don't already have. Learning comprehensions right now won't actually let you solve problems that you can't solve with for loops and accumulators. So they are technically redundant, um, but they're really cool. They can be really cool. I'm not throwing them under the bus, but they're a little extra. If you okay, also if I don't want to totally shut this down because I use comprehensions and I like them. If you stay on after class and ask me after class, I'll be happy to give examples. Hope that helps. Great. Wouldn't make in car search both keys and values. You know, it would be nice if that was the case, but that isn't the case. It searches only keys, and that's kind of I mentioned this before. Like if it were me making Python, I probably would have made this an error, and I would have made these. I would have just enforced somehow stating keys and stating values. In my opinion, this should give an error, and then if you want to do both, you can do .items. But you know, I didn't write Python, so it's still one of the best languages I've ever worked in. You know, it's not perfect, but it doesn't make every decision I would have made. But I don't really care that much. It's a wonderful language to work in. That's just one of those things. Like every language has like some of those things where you're just like, it's not what I would have done. But yeah. So just to reiterate this, the question is in regards to make in car to this line here, and the person is saying, won't this check both keys and values? And definitely I understand where that assumption is coming from, and to put that to bed right now, that this only will search keys. Don't mean to harp on that either. It's a great question. It's good to clarify that, but just to be extra clear on this, I'm going to do this. So these are exactly the same. I believe this is formally syntactic sugar for this. That is, when Python sees this, it rewrites it as this and interprets it as that. So anyways, good question. Yep. Somebody gave a much more succinct answer. If you don't specify it, it defaults to searching just keys. Yes. So default is just keys, .values searches .values, .items searches both. That is correct. Good. Great questions. This is great. It's great to clarify all this. I know I'm very like I can state things in a very like particular and very precise way, and sometimes I repeat things just to make sure that that understanding is clear. I hope it doesn't sound like I'm harping on anything, or like I hope it's not like embarrassing anybody if I repeat something or something like that. You know, I just want to make sure, since this is foundational stuff, I just want to make extra sure that what I'm saying is clear. But to be clear, these questions are great, and I appreciate you asking them. Cool. All right. So I think that covers keys, values, and items. Any last call for questions on these? Give you all a second. Feel free to put in a question on these if you've got them. I'm going to move forward though. Traversing a dictionary, this is just talking about using dot items. You can iterate through a dictionary without specifying dot items, but again, the assumption is that you're going to iterate through just the keys. If that's what you want to do, then well, this is one way to do it. But again, I would, if this is my code, I would always do this, just because I like to be explicit even if I don't need to be. It's better to err on the side of too clear, I think, in your code. Because why not? Like, I mean, it's a few extra characters, you know. If I'm making like super long lines that are just messy and pedantic, then that's one thing. But if I can make something a little more clear here or there, then why not? Okay, deleting key value pairs. So I think we talked a little bit about this. I mentioned the del keyword. I think I sped through this as fast as I could. This is the last thing we talked about last class. I'm going to use this car dictionary. I'm going to make it. I'm going to do it this way. Okay. Dang it. Let's say this. I'm going to do this. And model year. I'm just going to do that. Okay, here we go. So here's our car dictionary. So let's, first of all, we'll just prove that that's actually what it says it is, which it is, because that's what it says it is. And well, let's do a little breakout. I also see a question here. I'll take the question on the breakout. Who remembers what pop does for lists? Give me, in your words, what pop does. If it helps, you can think. I mean, you can put it in your words, but if you want a little bit of structure to that, you can optionally put it in terms of input, process, output, side effects. Oh, cool. Somebody's just saying good that I'm explaining, taking the time to explain the foundational details. Thanks for saying that. Glad that's helpful. Cool. Feel free to get your answer in. I'm going to kind of start reading through these. So, removes the last element and returns it. Pop, yep. Removes the element at a specified index and returns it. That element, yep. Pop removes the value at a given index and returns it. That value defaults to the last item. Yeah, yeah. Removes the element and returns it. Exactly, yeah. So pop is kind of a funny one because it's a mutable operation, meaning that it changes the type that we call it on. And it's the same for a list as it is with a dictionary. So if I do this, so I do this with a, oh, that's interesting. Huh. I wonder. I thought that would work, that would default with a dictionary. I'm actually glad it doesn't, because I think that should be an error. So that's actually kind of cool. So we need to specify a key to pop from. So let's just call this res equals, oops, car.pop. and we'll pop, let's pop model. Oops. So we'll pop model there. And let me do a before and after. So there's our before, and here's our after. Of course, I can print res as well, res. Okay, so notice we've got make Toyota model Highlander year 2011 color black. Then we assign card.pop model, which is Highlander. It pops off Highlander and returns it, captures Highlander in res. So notice it only captures the value, not the key. The key just goes away. This is kind of okay because Python's assumption is that you can, if you needed to save the key, well, you had to pass it in at some point. If it was important enough to save, you could save it there, right? You know, maybe we wanted res to be a tuple of key and value, I guess. Oops. We could say, well, let's do this. Key equals model. I don't think that's how you spell model. I never know where the E goes on this word. I like look it up and then it just, I don't know. Anyway, so since we have to pass it, we could recover it if we wanted to, because we have that information. In order to use pop, we have to have that information. So we can recover that key, but it just returns, notice it really does just return the value. Okay, cool. The other option is del. We could, I'm just going to do this. Just duplicate. I'll do pop. Pop key. And this will be del. Okay, so let's try this with del. So if I wanted to, we could basically recover the same behavior with del, just with an extra line of code. I could capture the model, or the the value like this, and then I could do del d sub key. Oh my gosh, my typing car sub key. There we go. It's a little bit of a distraction, I think, to have that res in there, but you know, like you can see with an extra step you can do all the same things. So if you want to remember one of these, it's kind of your choice. You can do either one, can do the other's job, sort of. Del is, you can see del's not a function or a method, it's a keyword. And it just deletes stuff. Just whatever you put after del just goes away. So I've done this before, but if I want to delete the whole dictionary, I can do that. And then when I try to print the dictionary down here, it gives me a name error, which is the same error as if I try to access a variable that doesn't exist. Name foo is not defined, so same deal. So del is very powerful. Very, very powerful. But you can use whichever one you like. Let's see here. We've got a little bit of, these are non-ASCII characters here. Let me grab these and correct them. So we got states. So we're going to talk about the .get method. And this is one of those power and responsibility kinds of things, like use this power with caution. Use it wisely. Okay, so state capitals dictionary. We've got Georgia, Atlanta, Colorado, Denver, Indiana, Indianapolis. These are the capitals of these states. So if we try to do D sub Colorado, no problem there. Oops, I'm just going to call this D. Let's try to print off. Okay, so Denver. If we try to do D sub Washington, we get a key error and it says Washington. It just says key error Washington. Key errors are usually Python errors are pretty, they give you like a sentence or something that kind of explains what the error is. A key error just says key error and then the name of the key that it couldn't find in the dictionary. And you just have to know that that's what it means. So when you get a key error, the thing that it tells you after it says key error is a key that it tried to find and couldn't find in the dictionary. So it causes a kernel panic. Couple ways around this. We could say state. Oh my gosh. Okay, let's try this again. State equals Colorado. Washington. And then we could do something like if state in d.keys. Now again, I could just do d, but I'm going to do .keys because that's what I prefer. Then we can print d sub state. And we can do that down here too. So this will create a little bit of safety. Check for membership, and we'll only do it if it's in there, right? I didn't get anything for Washington, so maybe what I want to do is say else. We'll say we'll print state not found. All right, this is a little bit, it's not a terrible amount of code, right? It's not a horrible thing, but we've kind of got some redundant stuff here. Denver, state not found, right? So this is a little bit redundant. It's not, like I said, it's not like really blowing up my code too much, but it's a little clunky. And this repetition, you might think, okay, well, maybe we could wrap this up in a function. It could take, let's call it def find, and it'll take in dictionary and a thing to find and an alternate, which we're going to start equal to none. So what I want to do here is we'll put the alternate here, thing defined is going to go in here, and then D, that's all set up. That's all good to go. And instead of, look, remember how much I say print is not return, and I totally almost let that print be my return, and it's not the same thing. Okay, return. Okay, there we go. Okay, so now I have this function. Now I can do this. So you got Colorado. Let's try find. Let's call it find thing. Okay. Find thing. So I'm going to say print find thing state, and we're going to do we're going to pass D and state, and alternate, which will be state not found. Okay. And grab this and bring this down. Okay. Cool. So now I have find thing. Oops. Here it is. Missing colon. Okay. So Denver is the capital of Colorado, and the capital of Washington is state not found, right? So this is kind of a nice safety. You could see how this kind of behavior might be kind of a nice safety net for accessing a key, right? So fortunately, as you may have gleaned, we don't need to write a thing finder function. We can do, let's see, how can I do this? We can do d get like this. This is going to have essentially the same effect. There you go. I wanted to build this out because there ain't that much to it, and it's kind of a good way of describing how it works. So basically all this does, all .get does, might be a little more complicated than this because it'll in here we can do, well, I guess this would work either way. In here though, we can do like function calls. So if I wanted to do what I want to do. I might want to, I can't think of an example that doesn't involve like something kind of complicated, but we can put a function call in here potentially as an alternate. Maybe it's a print, or maybe it's some function that has an effect somewhere else if we wanted to do that. But we can perform some alternate action. In this case, it's just an object to be returned, so state not found. Often you'll just give a message, or some other maybe default value, some safe value that you can return from this. So yeah, looks like I saw a question pop up real quick, and it looks like it went away, but okay. Is .get a method? Yes, .get is a method. It's a method of dictionary. So we do dictionary.get and then state. The way I wrote this find thing, this is just as a function, but yeah, .get is a method. Put a function in state not found. What did you mean? Sorry. We can put a function call here. I'm just trying to think of a good one that isn't weird and more confusing somehow. Oh, you know what? We could do something like, let's just do len. I don't know, len. We could have this function call len. This is actually, I was thinking that this wouldn't work for my find thing function, but it totally will. So this is going to be the alternate thing to return. Is let's do len of state. This will return. This will return the length of the string Washington in this case. So there are 10 letters in Washington, I guess. So it's just an alternate thing to return. Like if it finds a value at the key, then it's going to return that value. If it doesn't, it's going to return the alternate thing you told it to. If you don't tell it to return an alternate, oops, it's going to return none. Cool. Whew, we got so much to get through. So I want to wrap it up on Git. If you have a burning question, feel free to pop it in there. The kind of the use case that I find for Git is you're going through, you have some corpus of potential keys that may be keys in a dictionary, may or may not be keys. Git makes that process kind of easy. You know, if you want the value for all the things that do have keys, then you can collect those and do whatever you need to those. And if you want it to not throw an error every time you ask for something that doesn't have a key, or where every time you ask for a key that's not in that dictionary, then that just makes it easy. What I don't want y'all to do is start using Git every time you want to access a key from a dictionary. Generally, what the default thing to do should be is to just use the standard subscription syntax. They are different. They do serve different roles. You can't do, for example, like .git does not replace this, right? If I wanted to reassign something to that value, I still have to do d sub key equals value. I can't do d.get key equals value. That's not going to work. So you still this is still the thing that you should use for the default, but .get is specifically useful for the times when you just want to avoid that error. So that's why I'm a little hesitant to teach it, or well, I'm not like hesitant to teach it, but I want y'all to be a little cautious, because I don't want you want I don't want to teach you things that avoid errors and have you think, oh well, I'll just use the things that avoid errors because errors mean I'm a bad programmer or something. Like, if you're not getting errors, you're not programming. You know, you want to write your code in a way that if there's a problem, it throws an error, and that way, if you have an error, you can write your code in such a way that that error just naturally, that problem won't occur, right? In certain cases, you know what the problem is, and you know it's going to throw an error, and you know that you don't care and it doesn't matter, so you can use a little bit of error avoidance, but not as a default. You know, if you know what you're doing, if you thought about it and you're like, okay, I don't really care about this error, and writing around it is kind of a pain, so I'm just going to use .get or whatever other thing, you know. So if you've thought about it, then great, and if not, then you know, that's okay. All right, cool. We got a breakout. So make a dictionary. I don't know if this is gonna probably not come through. That did not come through. Okay. Let me see if I can grab this out of here. Where is it? There it is. Okay, you might need to copy paste that into your editor because it's a little smushed in there. But I will also provide, oops, a screenshot for this too, if that helps. Where is that? Cool, I'm going to put 5 minutes on a clock. Go ahead and start working through that. Okay, I just made a mistake. Sorry, folks. I went straight through this part on copying, and it's kind of useful for the next breakout. I'm so sorry. I'm gonna stop this breakout timer because we need to talk about copy. I was kind of looking through to see what was ahead of copy, and then I just kind of saw the breakout and got into that. So apologies for that. Do people remember what copy does for lists? And I'll give an explanation on this. We'll do the same thing as pop. What does copy do, and when would you use it? We'll treat this as the breakout. And for lists, think about it in terms of lists because we've talked about lists. If you frame it in a generic enough way, it should apply to dictionaries as well. Cool. We got a few answers. Keep them coming in. If you've got an answer, feel free to put it in, whatever it is. So it returns a copy of the dictionary, creates a duplicate version, copy creates another version of the object that has a different ID. Somebody's asking if it's a deep copy. Yes. I'm always kind of, it's pedantic, but I'm always kind of irritated. There's these terms, deep copy and a shallow copy. A shallow copy is not, there's nothing about a shallow copy that is a copy. It sort of is, it's a fake copy. It's an illusion that there's nothing being copied. What a shallow copy truly is when you have two identifiers, which are variable names, that both point at one object, the same object. So two names for one object. To me, I wouldn't call that a shallow copy. I'd call that a problem. More than likely, that's a problem. I'm not sure that there's ever a desirable, that's ever a desirable behavior. I'm not sure that it isn't, but I can't think of a case where that's necessary, and I suspect, frankly, that there isn't one. So when we talk about a deep copy versus a shallow copy, you'll hear those terms, but a shallow copy just means that you have two names for one object. That's really what it means. And a deep copy means that you've made a second version of something that is identical in value but not in ID, right? You can think about it like if you have two, and I use so many car analogies, I worry that you guys are gonna think I'm like a car person. But it's intuitive. So I mean, it's something like most of us, like drive a car or been in cars or whatever, and it's something that we live with in our daily lives. So if you have two cars that are the same color and the same make, same model, same year, maybe they rolled off the assembly line at the same time, right next to each other, right? You could say they're the same car, but they're not literally the same. They just have the same attributes, right? So when you copy something, you end up with something that has, quote, the same attributes, but it's literally a different object. And in your computer's memory, that's also reflected, where you have one region of memory devoted to the one object and then the other region of memory devoted to the other object. That information is literally duplicated. It exists in two places. And then if you want to change one, if you want to mutate one, that won't cause a mutation in the other. The reason that this is useful is that when we write functions and we pass in a mutable type as an argument to a function, we do not want that function to cause a mutation to the object that we passed in. Now, sometimes the process that we intend to perform would be greatly aided and would really be helped if we could mutate that thing. So rather than mutating the input, we just make a copy and we mutate the copy. And then maybe we return, probably if we went through the trouble of mutating it, we probably are interested in the value and returning it from that function. So frankly, it's most of the times that you think, oh, I'll need to do that, you can reframe the problem in some way that makes the whole thing easier. So a lot of times you think you need to use .copy, just give it a second thought and say, wait, is there an easier way that I could do this? And if you can't think of one, then go ahead and go with the copy approach. But yeah, at any rate, if you're not sure, I'll be precise about this sometimes, and sometimes I'll correct people's code if they're copying when they don't need to. But I will say this: so if I correct your code and I say, well, you don't need to copy here, I am telling you this. The safer assumption is if you don't know if you need to copy or not, just copy, because it's better to leave a memory footprint that maybe is a little bigger than it needs to be. If you're duplicating information unnecessarily, that's better than causing a mutation in something that you didn't want to change, right? So you might cause a little extra memory duplication even if it wasn't necessary, and like you'll get a hang of it, and eventually you get the feel, you'll get the sense, okay, I do need to copy here, I don't need to copy here. But when in doubt, copy, because it's safer. It's going to lead to more predictable code that's going to work more consistently, especially while you're beginning, until you get a feel for when you do and don't need to do that. Now, like I said, I know I'm telling you that that's the safe assumption. If you send me code and you're copying unnecessarily, I probably will point it out, but it's not meant to, to like tear down your code and say, oh, you're doing it wrong. It's just to help you get a sense of when to do it and when not to. Excuse me. Oops. So let's see here. Sorry, I was just getting a phone call. We've got a couple questions. Copy makes a copy. Oh, okay. Isn't there a deep copy function? I don't believe there is. Yeah, dictionaries do not have a deep copy. you might have heard that copy performs a deep copy. That's probably what you heard. So dot copy is what we call a deep copy. Like I said, you will hear those terms, deep and shallow copy. I find them misleading though, because a shallow copy is there's nothing being copied. There's nothing, if you look at what's happening, it would be incorrect to assess that there's any copying happening of any kind anywhere in a shallow copy. And in a deep copy, like, why not just call it a copy? Because it makes you think, oh, well, there's this kind of copy and that kind of copy. And a deep copy, it just means that it was actually copied. So you will hear those terms, people talk about it in that way. Let me show you a shallow copy, just because I keep talking about it. I'm trying to show examples rather than just talk about code, because it's kind of annoying to. I find it annoying when you know, like if I'm learning about something coding related and I hear somebody talk about it, and then yet here I am doing it, and I'm like, okay. So let's say let's call this car1, and let's say car2 equals car1. So if I say del car2 sub color, and I print car1, okay, this is a shallow copy. What does your intuition tell you? Is car1 gonna have color in it? So let's walk through this. I define car1, I say car2 equals car1. This looks like a copy, right? In the code, it looks like something's being copied, but it's not. It's an illusion. So I delete color from car2. What happened to car1? Did anything happen to car1? So here's the question. Does car1 have color in it? If I print car1, will I see color black or not? Yeah. No, due to the question setup. Exactly. Yes. Right. I I know I ask a lot of questions like this where I like lead into the answer, but it's like I still want you to like think about it. You know, go with what your intuition. Does your intuition tell you one thing, but my question setup tell you the other thing? So in this case, yeah, color is going to be gone from car1. So we printed car1 and color's gone from it. We'll print car2 just to prove that it had the same effect on both. So if I alter one, let's alter car1 now. Let's remove make. So it's altering, like the way this gets talked about is it's altering both dictionaries. There is no both dictionaries. There's not a second dictionary. The second dictionary is an illusion. This is what I'm saying. We have one object in memory, and what this syntax on line 94 does is it says point this identifier car2 at that object, and you also have car1 pointing at that same object. So you have two identifiers, one object, and they're both pointing at the same object. So if you change one, it affects quote the other, but again, there is no other. It's just the one thing. It just has two names. So hopefully you can see why I don't call this, to me, wouldn't really call this a shallow copy. I'd call this a problem. This is car2. Like, what's the purpose of this? Why have two identifiers for one thing? It's a little different if you have a function, you know, you have the parameter is now an identifier for that object. So that's technically a second identifier, but and you could think about that as a shallow copy, but really it's just the parameter is a second identifier pointing at the same object. So in this case, if I wanted to truly make a copy, I'd have to say .copy, and that is a deep copy. A deep copy. Cool. So if I alter one, it doesn't alter the other in that regard. The name should be overwritten. Yeah. Weird stuff. Cool. One of the other things, and I feel like I should just show this. Okay, so let's do this. Def make standard car. So we'll take in a car dictionary, and I'm going to give, we'll take in a car dictionary, which is just called D. And basically the goal of this is we just want every car that we pass to have a just make, model, and year. So if it has any other fields, we just don't want those reflected in the return. So I'm just going to return, I'm going to say 4k v in d.items. Oh shoot, I'm trying to show the problem here without using copy, but I am going to have to use copy because of what I want to do. Shoot, I can't do that, can I? Ooh. I'm just going to make this into a list. Okay. Don't ask me why. I'll explain later. So list of d.items, we'll do key and value in that, and then I'll say if k, so if our key does not match, we'll say not in, and I'll just do a list of make, model, and year. So if our key is not one of these, then I'll say delf, I keep doing that, del d sub k. All right, and then we'll return d. I know I say always write your tests first. You may chastise me. I have performed a hypocrisy, I'm aware. Okay, cool. So what do we expect this to return? It's not going to have color in it, right? That color is going to be removed because color doesn't match the ones that we wanted here. Does anybody see the problem with this? What happened to car, our initial dictionary, right? We have this innocent little dictionary. It's just hanging out, having a good day, and it just goes over to this function, and this function's like, bam, you've been mutated. So this function takes in this dictionary and it mutates its input. And to be clear, well, to be very clear, there are times where I've done this deliberately. If I make a function and I knowingly, intentionally mutate its input, usually what I'll do is I'll say mutable in the title of the function, or I'll say mut or something. You know, I'll usually put it as the first thing, not at the beginning. I'll put it at the beginning, not the end. That way I can't ignore that it's going to cause a mutation to one of its inputs. If I write a mutable function, I'll usually try to give it only one input. Preferably though, you never want to do this. I've done it before purposefully, but it was always something where I'm like, well, what I'm going to do is I'm going to do it this way for now, and then I'm going to come back and do it the right way later by making an extension class, which is a whole other can of beans that we're not going to get into in this cohort. But the short answer is you never want to write a function that mutates its inputs. You always want to avoid that. So the way around this is we can do d equals d dot copy. All right, so now if we run this, d returns a copy. Like that. Now, of course, the way to do this in reality is to make an empty dictionary, and rather than have a sort of reverse accumulator or a decrementation, sometimes it's called a decrementation pattern, where you start with something that has contents and you like remove contents. It's generally easier to start with something empty and build it up out of correct elements. So what I'm going to do is just invert this condition and say if the key is in one of these, then we'll say d sub key in our new dictionary. And let's do this. I'm going to call this dn. And we'll say dn. Oops. Sorry about that. So we'll say d sub key k equals v. So this is a nice, simple, vanilla, boring, straightforward dictionary accumulator. It's so straightforward, right? So we'll make sure that the key is valid. If it is, we'll add it in. If not, we don't need to worry about anything. We didn't have to do any copying. We didn't have to do any mutable, well, sorry, this is a mutable operation on this empty dictionary, but we didn't have to do any like removing from anything. The only thing is that we have this dn and this d. You know, we have to make sure we're operating on the correct dictionary here, but to me, code like this is standard and it's clear. And if you're working on something where you're reducing, if you have a dictionary or a list and you're reducing its size, you're doing like an anti-accumulator, just pause and think if you can turn this into a positive accumulator in some way. Just ask yourself, like, is there a way that I can conceive of this problem where I start with something empty and then I add in correct values? Almost always the code is simpler, safer, and often will have performance benefits as well. Sometimes you can't get away with it. Sometimes you have to do a reductive solution, but those times are rare. Generally, when you have a problem and you're like, I have to do this reductive style accumulator, most of the time you will be able to rewrite it as a positive style accumulator. So. What was the difference between the previous version? Will you keep the previous version code example? Positive, oh yes, sorry, yes. Let's do this. You know what, why don't I do this? Positive, positive. And then I will duplicate the whole dang thing. It's positive, and we'll do negative, Negative. So the negative way was, we start with this. We'll do dn. Okay, sorry. Funnily enough, we have to do .copy here. Here, I'll show you why. I should show you this error anyways, because it's kind of interesting. Oh. I was like, what's going on? Okay, so we get this special error. It's a runtime error. It says dictionary changed size during iteration. So you get this error when you try to remove elements or when you try to change the size of a dictionary while you're iterating through that dictionary. So notice we are iterating through d.items while we are deleting from d.items, right? So you might think, okay, you know, if you did it this way, at least you don't have to duplicate your memory footprint. You still do, though. That's the thing. You still have to duplicate. You still have to double your memory just so. Oh, excuse me. This has to be copy, and then this has to be items. Sorry. You still have to duplicate your memory footprint, and you end up with two of the largest forms of those dictionaries, and then removing from one of them. We could even do. This still has a mutation problem, so let's call this dn, and so we'll iterate through dn.items, and we'll say d equals dn.copy. So this is the negative form, right, where we are starting with d as a copy. We are iterating through dn. So this still doubles the memory footprint, and we're deleting from the copy, which, so this is safe now. It's not causing a mutation, but it's kind of clunky, and there's actually more memory duplication that's happening here than in the positive accumulator. And this is just simple, gentle, nice, easy, straightforward code. Empty dictionary, loop, easy condition, d sub k equals v. Standard, standard, standard. Whereas this is kind of weird. We've got del, I don't know. Cool. We're past time for a break. I still do want to have a little bit of a break. Yeah, let's just have let's reconvene at 23 after the hour. It'll be a little bit of a short break. Okay, cool. Sorry about the short break. It's 23 after the hour. Let's get going again. I'll give you all a second to sit down, catch your breath. Okay. So, we're going to change gears. I'm going to save those breakouts either for the end of today or for the beginning of next class, depending on what we have time for. So I want to switch gears into the set data type. Tovio will be, Tovio asked that I get through sets today because they will be teaching sets. Yeah, I think next class, but some point this week, not next class. So let's talk about sets. Let's do our overview really quick. I won't do the full thing, so let's talk about our types. Types we've talked about: int, float, bool, none, string, lists, dict, set. Cool, we're about to talk about sets, and then the only one left will be tuples. Hopefully we'll have enough time for sets and tuples. You've heard me talk about tuples, you've seen me give examples of them, I'm sure you've seen them and learn. You're working with them whether you know you are or not already. They are like lists. If you have a clear understanding of mutability and the mutable aspects of lists, just think about a tuple as a list without the mutable aspects. It's essentially what it is. If you take a list and you remove the immutability from it, you end up with a tuple. So that's why I'm doing this one last, because most of it you already know. We will give some examples though. So that's where everything fits together. We just talked about dictionaries. We're going to talk about sets. So sets are another mutable type. So sets are an unordered mutable collection. Mutable meaning that we have mutable operations. We can add to them, we can remove from them. Sets will only contain unique elements, so we cannot have duplicates of the same elements in sets. And it doesn't say it here, but sets can also only contain immutable types. So if you think back to dictionaries, when we talked about dictionary keys, dictionaries, it's been a long time since we talked about dictionaries. If you think all the way back to dictionaries, dictionary keys are can be any immutable type, and they have to be unique. Keys have to be unique. So that's kind of what sets are. They're kind of like the keys without, or they're kind of like dictionaries without values. I heard some cheesy joke like, why are dictionaries better than sets? Because they have values. I don't know, some cheesy Python joke. So sets are like the keys portion of a dictionary. It wouldn't be, if you do like dictionary.keys, that, to be clear, that's not a set, but there's an analogy to be drawn there. Okay, so sets are unordered, mutable, like again, like dictionaries in both of those regards, and they will contain only unique elements, and the elements that they are capable of containing are only immutable types. Sets can be declared using the set constructor function. They can also be declared using curly brackets like this, but as you may notice, curly brackets are what's used to delimit a dictionary. So if I try to make my set and set it equal to like an empty set like this, Python's going to think this is a dictionary. So to this point, there's always been a literal form that we've had for every type. Sets are going to be the exception. So when you make a set, you can say set like this, and then you can pass it if you want to do a list or a tuple, something like that. Let's just try. I'm not sure if you can just pass it stuff like this. Let's just try that. I think that's going to give me an error. Yeah, so set only expects one argument, so I'd probably make it a tuple. So just a second set of parentheses. Looks a little weird with the double parentheses on each side, but the inner part is a tuple. The reason I'm not using a list is lists are this big, burly, complicated type with a whole bunch of features that we don't need for something that we're just going to instantly cast to a set. So tuple is a lightweight, nice little type that is quick and easy to set up in your memory and comes and goes, makes a lighter footprint. So I'm going to use a tuple there. So it doesn't really matter though. You could do a list, just to be clear. It definitely looks better. It definitely looks like I'm passing something and not just have like meaninglessly duplicated parentheses, but either way, 6 of one, half a dozen of the other, doesn't really matter. So if I print this set, okay, so given this definition of the set, what is this set going to print? When I run this code, what will it print? Also, can people see it? Maybe I need to blow up my text a little bit. Okay, cool. So let's run it. Oh, oops. I was like, wait, what? I passed the set function, not my set. There we go. So we get 3, 4, 5. So notice they are in order. I've noticed recently that sets are now being like printed and iterated through in a sorted fashion. If that's important to you, I still think about them as not having an order, so I just don't think about their order as mattering. But I don't know, maybe that would change something. But so in this case, you can see it's delimited with curly brackets like a dictionary, which is a little confusing, but that's how it is. When a set gets printed out, it'll have curly brackets around it like that. The elements will be sorted, not that that matters. And even though I put a 3 in here twice, there's only one 3 in the set. And that's because sets will only contain unique elements. We cannot have duplicate elements in a set. And that's why it's a set. Essentially, that's why it's a set, right? If you have, when you're talking about set theory, you know, if you have a set of one, you know, you have one set and another set, that set includes all the elements within it, but it's not meaningful to include an item more than once to define the set, right? You know, the set of all numbers between 1 and 10, let's write the set of all numbers between 1 and 10 inclusive. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the set of every single number between 1 and 10. It would not be meaningful for me to like add in, you know, well, 1 is in there, so might as well just stick that in there again. It wouldn't, you know, that's not useful information. It's still the same set whether or not it has duplicates or not, so we don't include duplicates. We necessarily do not include duplicates. So a set does not include duplicates. So this is a set of numbers. Let's just make it clear though. Let's say hello world do this. Okay, so we turned this string into a set. Now we have a set of characters. Weld space row. Is this actually gonna? Oh, yay. Okay, so it actually is, it's gonna, oops. Okay, sorry, I messed up my file watcher. So it actually, you can see with a string, it's actually giving me a different order every time. So if I run this, right? So it's giving me the orders or the letters out in a different order every time. So this is what I mean about if you're thinking, oh well, I can count on the order being like this or being like that, right? Just don't count on the order being anything that you can predict, because there are times when it's going to be different. So if the order does matter, you can look up like if it's a set of characters or a set of numbers, whether it's going to retain an order and how that order is going to be administered. Is it the order that they were added into the set? Is it the sorted order? Is it lexicographical order or whatever? So a set of strings does not retain an order. And let's do another one. So hello, hello world gives me a set of hello world, hello world, hello world. It really wants to give it in that order. Oh, there's world hello, world hello. Okay, so you can see the order is arbitrary with this as well. There you go, sets. All about sets and set things. So removing duplicates. So sometimes if you have a list of immutable objects or a tuple and you want to remove duplicates, you can cast it as a set and back really quick. You're probably going to lose the order the elements were in. Well, you may lose the, well, whatever order they were in as a list or a tuple, you cast them to the set, they're probably going to be in a different order. When you cast them back, they may yet again change order a second time. So if that doesn't matter to you and the only thing that matters is removing those duplicates, then great, that's fine, that's going to work. If the order did matter, then you have to find a different way to remove duplicates. The set will not work. Find something else to do. Fortunately, writing a for loop to like accumulate, you know, it's pretty straightforward to just write a function that just takes in a list and returns a list without of the same elements without duplicates, right? So you all could do that probably pretty quickly. But sets do remove duplicates. So so sets are this weird type, right? They can't have duplicates. They don't have an order. You might notice, well, if it doesn't have an order and they don't have keys, or they are keys and they don't have values, and it doesn't have an order, like what mechanism is there, like an index or a key, so that once I have an item in a set, I can get it out again? And there isn't one. Sets don't have such a mechanism. Lists and tuples and strings have indices. Dictionaries have keys. In all of those cases, we can store in elements or values and recover them later via the key or the index. Sets have no such mechanism, so they're not useful for that. They're not useful for, you know, collecting things and then recovering those things later. Generally what you do is you work with lists or tuples or dictionaries, and you cast things to sets momentarily as needed. that cast doesn't like change a dictionary, or excuse me, I'll use a different example. It doesn't change a list or a tuple. It doesn't change that into a set. It still leaves that list or that tuple or whatever, and then just gives you a different object that's a set of whatever the elements are in that thing. So you do a set transform on a given object, you get a set back, you do whatever your set operation is that you need to do, and then you're done. That's one way we can think about using them. So for that reason, I don't find myself like writing set accumulators that much. Occasionally I will, but I don't do it as much. What I'll usually do is like a list accumulator and then just cast it to a set and do whatever I need to do with it as a set, and then off to the races. So that's one way you could approach set accumulation, is just list accumulation and then cast the list as a set. Okay, so we've got this really weird type that doesn't like, we can store things in it, but we can't retrieve them. The things don't retain an order. Sometimes they come out in a random order. They can only contain immutable objects. So like, what are they useful for? Why would we ever want to use this terrible type? Well, sets have these methods: union, intersection, and difference. And let's actually just look at this really quick. They have quite a number of methods, but these are sort of the ones to know. These are very useful. So let's do directory of set. Oops, there we go. You'll see we have quite a lot of set methods here. Not a whole bunch, but we've got add, clear, if you know what clear and copy do for lists. They do the same for sets. Copy, we just learned about copy with dictionaries. So you'll notice all the mutable types have a copy method because they're mutable. So it's sometimes we want to copy them and make a change to the copy rather than make a change to the original. Difference update, discard, intersection update, is disjoint, is subset, is upper set, pop, remove, etc. So there's a number of methods here, but the three important ones are union, intersection, and difference. If you want to learn about the other ones, it won't stop you, but these are the ones we're going to cover. These are the ones we want you to know. So let's make a set. We need two sets, I guess. So let's do union. So union, the union of two sets is all of the elements that are unique to both set 1 and set 2. All right, so let's do this. Set 1 equals set, we'll do a list of okay. And let's do the same thing here. Okay, this will be set 2. So we've got set 1 and set 2. These are both kind of big for single digit numbers. Let's just do something like this. I don't know why I have duplicates in here. Let's just get rid of those duplicates. I don't need to do anything fancy with those. So 4, 5, 3, 6, 0, 9, 2, 8. And let's make sure that there's a duplicate. We'll say 7, and this one will have a 7 too. Okay, cool. So let's print the union. So sets union. I'll just capture it in a variable. I could print it off directly. So I'll say set one dot union set two. And just to be clear about this, it doesn't matter which order we do it in. This is not a mutable operation. It returns a set, like I said, that contains all of the items that are unique to both set 1 and set 2. Oh. I said I would capture it in a variable, but you know what? I'm just going to print it off. We're just going to do it that way. So you can see we get the same result either way, right? So 0, 2, 3, 4, 5, 6, 7, 8, 9. Oh wow, I literally got them all in there. So 0, 2, oh, we don't have 1. 0, 2, 3, 4, 5, 6, 7. You can see there's 7 in there twice. 8, 9. Now you might ask yourself, which 7? Is it this one or this one? These 7s have the same ID. It looks like when you have an immutable type that shows up, the value for that type shows up more than once in the same scope, it'll have the same ID. So it doesn't matter. You can think about it as just pick one, or you can, the reality is that's the same 7. There's only one object in there. There's only one 7 object in there. So that's union. Another one is intersection. So intersection is all of the ones that are in common. So let's do this, intersection. Intersection, right? So the only element that's in common is this 7. Maybe let's do a 2 in both of them, right? So 2 and 7 are now the only ones that they have in common. So when you see intersection, think what do set 1 and set 2 have in common with each other? And that's what you get back for intersection. Lastly, we've got difference. Oops. So difference, oops, helps if you put in all the letters. So the difference, so notice that difference gives me a different result if I do set 1 difference set 2 versus set 2 difference set 1. So the order does matter with difference. It does not matter with union and intersection, and that's why I was showing either, you know, set 1 set 2 or set 2 set 1. Something that's kind of convenient with difference, and again, I believe this is syntactic sugar. We can just use the subtraction operator like this. Set 1 minus set 2, set 2 minus set 1. And this is generally what I prefer to do. I think it's a little cleaner, and to me it says difference, but as you might be able to infer, set 1 minus set 2, or set 1 dot difference set 2, is all of the elements that are in set 1 only, and if it also shows up in set 2, then it's going to exclude it. So notice if we look at 2 and 7, right? So 2 and 7 show up in both. So all of the elements that only show up in set 1 are 4, 5, and 6, right? Because 2 and 7 show up in set 1 and set 2. And the reverse is true. Set 2 minus set 1 is all of the elements that show up in set 2 that are not also in set 1, right? So 2 and 7 again are in set 1, so we're going to include 0, 9, and 8 as the elements in set 2, or as the difference of set 2 minus set 1. We got a question here. It says yours didn't print in order. Yeah, so or sorted. It depends on your version of Python. a year ago when I started teaching premium prep, I used to be like, hey, sets and dictionaries, here I'm going to show it to you. We're going to make a set or a dictionary, and no matter what I put in there, it would print out in a different order. And as of November or December, I think the change was made in November, but I noticed it in December of 2020. I noticed it in premium prep. I was like, okay, dictionaries are an unordered type, and I went and I printed out a dictionary, and it's like, see, we're gonna run it again, and it'll give me out a different order, and it gave me out the same order, and I thought, well, what's wrong? This is such a strange thing. So I know that they've been making changes pretty recently to set and dictionary ordering rules. I don't know if they're going to end up being indexed types. I somehow doubt that that sets will have indices in the future. I don't think that's going to happen. What I think will happen is that they will, like, eventually it'll become standard that they will retain some predictable order and the ordering rules will be predictable, but it's likely that you have an older version of Python that isn't reflected in, which is fine. Whether or not it comes out ordered or not, you still think about it as not having an order. Just, if you're looking at this and trying to understand when is it in this order or when is it in that order, just don't worry about that. Just think about, like, whether or not I see it come out in an order or not. If I want an ordered type, I'll use a type that has an index, like a list or a tuple or something. So that's what I suspect is happening. Hope that helps. Okay, we've got 10 minutes left. Do this breakout, or we could talk about tuples. I kind of want to talk about tuples on Saturday. Well, we'll go over this. Well, I should just briefly mention them, but I have sort of a little example thing that I like to do with tuples. It's not that big of a deal. Let's just talk about tuples really quickly. If anybody has any set questions, feel free to pop those in, and I'll get to those as soon as I can. Tuples are an ordered collection. So they do have an index. They're very similar to lists with two key differences. They are immutable, and they're declared using parentheses. We can index and slice tuples because they are ordered. So if you understand indexing and slicing for lists, you understand indexing and slicing for tuples. They work exactly the same way. Tuples only have two methods associated with them. So let's look at this. Come to our Python shell here. Let's do dir of tuple. So look at that, count and index. That's it. That's all we have. We don't have a copy. We don't need a copy because they're immutable. We don't need to worry about them being copied or whatever. So count and index is all we need. Yeah, that's all there is to it. So they might seem kind of weak, like why would you ever want to use a tuple over a list? Like I said, like if you're trying to, I gave some examples up here. Yeah, like right here, here's a good example. Right, I have this list that's just sitting in my memory. Well, this list is, like I said, it's a big, powerful data type that has all these mutability features, and all I'm doing is checking membership in it, right? Well, a tuple is more easily allocated in memory. It's more easily deallocated. Since your computer doesn't have to think about how do I put this in memory in a way where I can later come back to this and change its size, add elements to it, remove elements from it. change the size of an element within it, whatever, it's like, oh, well, I know how big this thing is because it says right here. So I'll allocate exactly that much memory and I'll stick the tuple there. And it's very simple. It's a very simple data type, makes a light footprint in memory by comparison to a list. I mean, when you have an element with 3 objects in it, or an object with 3 elements in it, whether it's a tuple or a list doesn't really matter that much. But if I was doing this, I was making like thousands of little tiny lists, it might add up. I might reconsider making thousands of little tiny tuples, and that might give me a performance boost. But that kind of like optimization kind of thinking, it's really cool. I like that kind of problem solving, that kind of thinking. But often it's something that you don't really need to concern yourself with. Often performance isn't as big of an issue as you might think it is. Not that it's utterly unimportant. It can be very important, but usually the first goal is to just make it work, and then if you can make it faster, then great. So yeah, that's one advantage of tuples. The other advantage is, the example that I gave with the function that mutated its input. That kind of behavior is impossible with a tuple. If I pass a tuple to a function, and then inside that function I perform some transform on that tuple, any operation I can do to that tuple is an immutable operation that may result in another tuple. I can concatenate against it and kind of use that as sort of an accumulation pattern. So yeah. So let's just write a real quick tuple accumulator. So I'll just call this tup. To make an empty tuple, no big surprise here. We make just parentheses like this, and let's just say we'll accumulate squares. We'll say for num in, and I'll do a tuple of numbers. We'll do this. Then I'll say tup plus gets another tup of num squared. Now here's one weird thing. Here's one little weird thing. So this num squared is going to evaluate to a number. So one number, it's going to make one entry in this tuple. What this line is saying is tup equals tup plus num squared. Now I would write this as plus gets like that, but without the second tup because that's convention. But I'm going to leave it like this just so it's extra clear what's happening. We're concatenating the current state, which is empty, to another tuple, which has an object in it. Now here's the weird thing. If you have a tuple with only one element in it, you have to put a comma after it. If you want a simple rule of thumb, just always put a comma after every element in your tuple. You might end up with a tuple that has an extra comma at the end, but it'll work. Oops. All right, so this is an operation that may look like a mutable operation. We are losing this original empty tuple. We're losing access to it because we're modifying its identifier. But that's the thing, is we're modifying the identifier, not the tuple. And what that means is if I have this tuple, say this tuple here after it has been populated with these elements, if I pass this into a function, let's just do this, tup equals this, print my function, we'll take in tup, let's call this my tup, and we'll just do this. Def my function. We'll take in tup. And we'll return tup like this. So we'll take this in and we'll modify it according to this, right? This is kind of a silly function. I'm kind of just duplicating whatever's in here. Oh gosh, this makes more sense like this. So if I do that, and then let's print my tup like that. We're going to see my tup was unmodified. And I am accumulating on my input. I'm literally accumulating on the input. Like in a mutable context, there could be no more like kind of obvious faux pas than this, but with a tuple, I can't hurt it, right? I can't alter this original tuple, not even if I wanted to, not even if I tried really hard, it's immutable. So it means they're safe, they're easy to use, they're safe. You can, with things like this, with concatenation, slicing, and indexing, you can end up performing most of the same operations, the mutable operations that you're used to with lists, with tuples, if you're creative about using concatenation, slicing, and indexing together. Those are very powerful systems, especially when combined. So cool. We are almost exactly out of time, so I will wrap up there. We'll do a little more on tuples, and we'll do those breakouts, those dictionary breakouts next time, and we'll just have a bunch of function practice and breakouts on Saturday. I know there were some lingering questions. Let me wrap everything up with the recording, and we will go from there. Just 1 second.